The name of this video is Shell Energy. This is an example where we use both expressions for the electrostatic energy for continuous charge distributions to find UE. We know that in a 3D, UE can be expressed as 1/2 always volume integral on the region capital omega where a charge ρ is distributed times the electrostatic potential V, the R capital Q cube vector. So in this case, we need to know, if we want to use this expression, we need to know everything about ρ. Okay? I also told you that, in principle, we can extend this capital omega to become any universe volume, capital omega infinite, the entire universe. Again, if you do know ρ, it doesn't matter if you do the integral just where ρ is localized, where it's located, or everywhere in space, because outside this point, capital omega, ρ is 0, so there is no contribution to the integral. This we need it eventually to prove the other form of UE, which involves E squared. We will come to that in a minute. Before doing that, though, what happens if instead of having ρ charge distributions, we have small sigmas on a capital sigma surface? Can we use an expression for that also for continuous charge distributions? Yes, in this case, UE becomes, we have done this in many different cases, right? So we went from a linear distribution to a surface to a volume. This is for volume. For a surface, it would be obviously 1/2, as always. In this case, the surface integral on the entire surface, capital sigma, of a small sigma times the electrostatic potential times dr square, capital Q. Okay? Infinitesimal area element. And again, also in this case, this capital sigma, you could extend it, but anywhere outside this, the point on capital sigma, small sigma is 0, so it's sufficient to do it on capital sigma. The extension is needed for the expression with E squared. Okay? So that's why we need the extension. So let's now try to use this expression for a surface. And so, for example, let us consider a charged shell, which is empty inside. So the shell looks like this. This is the center of the shell, which has a radius capital R. As always, we choose a spherical coordinate system with coordinates R and theta and var phi as well. This is the origin here. Suppose that this shell is characterized by a uniform surface charge distribution with density small sigma equal constant. And suppose that this sigma is continuous C naught on the entire surface capital sigma, so it's well behaved. So because of that, we can kind of use also the expression for E, which I'm about to consider in a few minutes. Under these conditions, we know that the electrostatic potential for a shell of this type, so let's write it down here. So the electrostatic potential V at any point in space is only a function of R because of symmetry reasons, and is given by, inside the shell is constant and is given by sigma divided by epsilon naught times the quantity capital R, which is the radius. So it's the same all the way to the boundary. And so we know that the potential is continuous. So this is for R from 0 included to capital R included. And outside is of Colombian type. And so it's a sigma divided by epsilon naught is a potential of Colombian type, capital R squared divided by small r. And this is for each point R between capital R included all the way to plus infinite. And as always, I'm including capital R because the electrostatic potential is a continuous function. All right, so we know that in fact, right on the boundary, capital sigma, the potential is sigma over epsilon naught capital R. So right on this surface, this is what we get because R is included. Okay, so now we want to remind ourselves what is accordingly the electrostatic field E, which is a vector, only function of R, directed as UR. So this one is going to be simply 0 within this region. So I'm not going to rewrite this because it's the same. whereas, because of course the derivative of constant is 0, so it's 0 inside, also from Gauss's theorem and symmetry arguments, whereas outside is going to be Colombian type, so it's going to be sigma divided by epsilon naught. Colombian type in this case means capital R square divided by what? R square, small r square, okay, directed as UR. Okay, again in this region here. So these are my potential and field. Okay, so now we want to use this expression to find, for which we need sigma, which is constant, and V, which we know, to find the energy. So let's spell it out here. So by using this expression here, which means this expression here, really, we obtain 1/2. The surface integral becomes the integral on the surface capital sigma, which means from 0 to 2 pi d bar phi, integral between 0 and pi in d theta of sine theta. We are right on the surface. The infinitesimal element is capital R square. So we took care of all the infinitesimal area element on this surface with the 1/2, which we didn't forget. So this is all taken care of. We need to remember that there is a sigma here, which is constant. What about the potential B? The potential B is right on the boundary, sigma over epsilon naught times capital R. So we have an R cube here. Okay, so this one simply gives us, as a result, 1/2. This integral gives me a 2, so 2 and 1/2 cancel out. This gives me a 2 pi. So I obtain 2 pi from this integral here, times sigma square here, times R cube, capital R cube here, divided by epsilon naught. Great. So we found the energy, the electrostatic energy associated with this shell. Again, if you were to compute it outside the region capital sigma, here sigma is equal to 0, so it does not contribute. So that's why we just can do it just on capital sigma. The extension, however, is needed when we want to compute the energy UE by means of the expression which we can use in this case, because sigma in my space here is a continuous function. So let's try to use the expression 1/2 epsilon naught volume integral on the entire universe. Now we really need to go in the entire universe. And why is that? Because we, in this expression, which features E square drq cube, here we don't have any rho in this expression. We forgot the role of rho. Okay, so since we don't have it, we need to integrate over the entire volume, otherwise it's pointless. And also this is the way we actually computed, we found this expression, which again, I specialize now to this case. Okay, so in this case, when we compute it, we need to use the expression for E, which is given here. So we are in the entire universe. Okay, so if we are in the entire universe, let's remember we need to do a limit. So we need to do the limit for small r, the entire universe. We consider it again as a super sphere with a certain radius here. So this is our sphere. It's an infinite sphere. Okay, an infinite hard sphere. So we need to integrate everywhere within this infinite sphere. So in the limit for r that goes to plus infinite, otherwise it would not be an infinite sphere, of 1/2 epsilon naught. Okay, here. Then we have now the integral between, as always, 0 and 2 pi. We need to use an infinitesimal element in a spherical coordinate system, d bar phi, 0 to pi d theta sine theta. All right, so now we have finally the integral between 0 and r, which eventually goes to infinity, in dr of r square, and this is all our infinitesimal volume element. So we took care of 1/2 epsilon naught the volume in dr cube times E square. E, of course, is 0 inside, so the only region where we are interested really is from capital R all the way to small r, which eventually goes to infinite, because the field is 0 inside. And so here we need to do this quantity square, because it's E square. So we end up having sigma square divided by epsilon naught square times R4 over R4, capital R4 divided by small r4. Okay, so this r square and this r4 here becomes a 2. So this limit eventually, so what do we get? We get the limit for r that goes to plus infinite of 1/2 epsilon naught 2 pi times 2, so 2 and 2 goes away, so it's 2 pi epsilon naught. So far this is 2 pi epsilon naught. But then we have 1 over epsilon naught square. So 1 over epsilon naught square, this and this go away. So we took into account this is 2 pi, this is 2, 2 cancels out with 2, so this is all there. Now here we need to have the integral of sigma square, so epsilon naught square we already took it into account, so sigma square is a constant. R to the power of 4, capital R to the power of 4 is a constant. So we need to integrate 1 over r square, which is nothing but minus 1 over r from capital R to small r in this limit. Okay, so if we do this integral in this limit, we need to do minus 1 over r when r is to infinite, which is 0. So the first limit here, this one gives me a 0 contribution. Whereas here, this limit gives me minus minus, because it's the first one, 1 over capital R. Okay, after doing the limit. And so, once again, we obtain 2 pi here times sigma square times r4 divided by r, which is r cube, exactly as here, from the integral, divided by 1 single epsilon naught. And so, beautiful enough, we were able to show that these two results are exactly the same. So, the two expressions, as expected, are equivalent, okay? So, we found exactly the same expression. In particular, so to re-summarize this video, we sort of extended our knowledge of how to find UE for continuous charge distributions from a volume to a surface to make it a little bit more spicy. Then we use this general expression for the surface, where sigma is only defined on this boundary on capital sigma. So we need only to integrate over that region up to small r equal capital R, which gives us this result. Then, since sigma is C naught, we can also use this expression 1/2 epsilon naught E squared, where we forgot the fact that actually there is a, well, in this case, more than a rho, of course, it would be a sigma if you want, and we forgot our knowledge of sigma. You see, there is no sigma here, it's built in, encoded in E. So in this case, we must extend all the way to capital omega infinite. And so when we do that, this is the limit to infinite over an infinite sphere. We obtain this integral when you need to remember to square the field here, the electrostatic field. And this integral gives exactly the same electrostatic energy as expected. That's it.